So sadly, we can't see Christopher when he speaks, but we can see him after. I don't know why, but we see your slides, Christopher. So
okay. Can everyone hear me?
yes, we can.
At
Yes.
least.
The 2 screens, isn't it?
Okay.
Okay, Christopher, you can go on.
You want him to start without being able to see him?
I don't know. Like, do you know how to see him? We will try to make you to see you.
No worries.
I tried everything. I have no idea. Usually, just by default, it shows. Okay, like that maybe. Better
It's a
than
bit
nothing.
imperfect, but it's better than nothing.
Yeah.
Possibly.
Also, I will maybe should clear my. I will just close my email so the rest are sounds.
I mean, if I do
Okay.
this, can you see?
Yeah, it's fine. We know sort of see you.
Okay, so I'll just have, hopefully, I don't know if there's anything important on my slides. Hopefully
There's
there's-
nothing like. So
It's not. There's not. It normally is, but it's not there. Right?
yeah.
I think it's something.
Christopher, just go on. We are already behind time. So let's. Okay.
Okay, sure. So just to double check, everyone can hear me, and can you see my cursor at least?
Yeah.
You can see my cursor. Okay, good. Super. Okay, so thanks, Tatsa. So today I'm going to be talking about some modeling work that I did while I was a member of Alex Wargar's group at the CBU. But since it's Methods Day, I'm really going to kind of give more of an emphasis on how plastic attractors work in working memory attention decision-making, rather than any particularly novel findings within these fields, although I will kind of gesture to some. Okay, and I should say, I think I was originally going to be in the neural modeling section, but because I'm in Australia, that would have been in the dead middle of the night. So Olaf very kindly agreed to move me into the morning slot. So thank you for that. Okay, so let's get started. So plastic attractors were really introduced into the literature by Sanjay Manohar in a 2019 paper as kind of a unifying model of working memory and object-based attention that incorporates both kind of delay period activity and activity silent mechanisms. And what was really novel about this model is that it really only has 4 major components, namely conjunction unit, the 2 types of neurons, conjunction units and feature units, which I'll go through in a moment's time, and lateral connectivity between conjunction units, which is all-to-wall, and lateral connectivity between feature units, which is just within the modalities. So color inhibits one another and shapes inhibit one another, but not like vice versa. And so conjunction units represent kind of neurons in PFC that have very flexible selectivity profiles that are adjusted in line with task demands. Whereas feature units represent kind of neurons in sensory cortex or various parts of sensory cortex with kind of fixed receptive fields. And they are connected through bidirectional all-to-wall connections, which are modified through Hebbian plasticity. And that's it, that's the model. That's all there is to it. And what's lovely about this is, despite the simplicity, it can account for something like 34 findings in the working memory literature, despite its simplicity. And in addition to that, it can also, without any modification, be extended to some very simple kind of decision-making tasks. And again, without modification, it can be extended to account for findings in the visual search literature. And with some minor modification, it can be extended to account for feature-based attention, which is really kind of my rather minor contribution to all of this. Okay, so how does this model actually work? So there are, as I said before, there are 2 key types of neurons in the model, conjunction neurons and feature neurons. And they are, the evolution of these neurons is described through these 2 coupled discrete time update equations. And I'll just kind of go through it piece by piece very patiently. And hopefully it should make some sense. So the first component is really just external input into the network, which is really just, it's a one-hot vector. These are just constants that get put into the feature units. And that's noted I external. The next is the baseline firing rate. Baseline firing rate is really just determines kind of the point at which lateral connectivity, like lateral inhibition between either feature units or conjunction units kicks in. When neurons fall below this value, they can no longer inhibit their neighbors. Next feature is really, and this is a really important feature for the operation of the model. When you remove it, it no longer works, is the saturating nonlinearity, or this is the activation function. And it keeps the model, or keeps the activation between 0 and 1. So it's this piecewise function that's, for people who are familiar with RNNs will know this is essentially just a ReLU, but this has kind of a maximum saturation value, namely keeps activity bound between the values of 0 and 1, and when it's between those values, it's linear. But if it falls below, but then it caps out at those values. Okay. The next component of these models is the lateral connectivity. So within feature units, say color or shape or position, these will inhibit within modality, inhibit each other within modality, and there'll also be an element of self-excitation. In the conjunction units, and this is really important, inhibition is all-to-all, and this gives rise to winner-take-all dynamics. Then and this is really the last component of the model, it's the Hebbian plasticity. And this is randomized, initialized with random connectivity. It's all-to-all, and then it's modified through a very simple covariance update rule. And that's it, that's all there is. And what I'm going to show you is that despite the simplicity of this model, it really is only 4 equations, or 5 rather, where we're going to be able to account for findings in working memory, some simple decision-making paradigms, and feature-based attention, and do so in a way that hopefully speaks to a link between kind of cognitive theories and neural data. Okay, oh, and I should say the last feature is just a couple of constants. These alpha parameters here describe self-excitation, lateral inhibition, and the synaptic gain of this Hebbian matrix. Okay, so we'll start with working memory, because I think this is what the model was designed to do, and I think it's kind of the most intuitive way to figure out how it works. And so this is the task that kind of used throughout Sanjay's 2019 paper. And here he presents a sequence of stimuli in a delay match to sample task. And each stimulus consists of 3 features, namely it will have a color, it will have an orientation, and it will have a location. And so each stimulus is presented, and and you can kind of see, if you look at where my cursor is, that the conjunction neurons will compete to represent it. And the winning conjunction neuron will be bound through Hebbian plasticity to these 3 inputs. So in this case, it would be red, 90 degrees, and top left. And whoops, there'll then be another 3 objects presented, a gap, and a probe consisting of just one of the features will be presented. And through pattern completion, the other 2 features are kind of reignited. And that's really taken as performance, or our measure of performance in this working memory context. And kind of give a feel for some of the results. And this really is just the tip of the iceberg of what the model can do. As I said, there were 34 findings. This is just 4. But so kind of we've got on the left-hand side of all of these different kind of comparisons, we've got the model, and on the right-hand side, we've got data, or some empirical data. And so as set size increases, so the number of things you have to remember, accuracy decreases. As you kind of decrease the serial position, so in terms of the last thing to be kind of maintained or encoded, accuracy decreases, and you also see this kind of kink that's qualitatively produced in the model and in empirical data. Encoding duration, accuracy increases as a function of the amount of time you're allowed to kind of encode something. And finally, kind of as the amount of time that you actually have to hold something actively in working memory for, that is the memory retention interval, as that increases, accuracy will decrease. And again, we see the same qualitative pattern in both empirical and model data. Okay, so what about decision making? So this is a very, really, all that it takes, there's only semantic modification to the model to account for decision making. And the semantic modification is really just adding 2 motor units, where these are just feature units identically. I've put them up the top of the kind of diagram for clarity, but they're identical to feature units. And they are bound in the same way that feature units are bound in the working memory example. Namely, we co-activate a stimulus with a motor action. And what that leads to is kind of a routing bound or through the conjunction unit between a stimulus feature and a motor unit or a motor action. And so the example I'm going to show you right now is just a really super simple, like the simplest possible decision-making paradigm you could possibly have. But they can get quite sophisticated, or the model can do much more sophisticated things. So this is really just to kind of get a feel for how the model operates. Okay, so just kind of show you. Presenting a stimulus with a button, stimulus 2. There's now a delay period. Present the stimulus, and through pattern completion, the model will reactivate the previously paired motor action and just kind of talk you through. So on the bottom here, we've got feature units. In the middle, we've got conjunction units. On the top, we've got motor units. And so what this kind of paradigm is doing, I'm not sure, there were air quotes around paradigm. I'm not sure if you can actually see me because it's so simple. But so we have a stimulus that gets bound up with a motor action and through the conjunction units, and there are 2 of them. And then when we represent just one of them, so just the green, the relevant motor action is kind of reactivated through pattern completion. And if we then take essentially the time it takes for this motor unit to asymptote essentially, so time to converge to its final value as our measure of reaction time, we can reproduce a very well-known finding in kind of perceptual decision-making literature, namely Hicks' law. And this is essentially the finding that as you increase the number of options or choices that you're deciding between, you will get a linear increase in reaction time if you have a if your x-axis is logarithmic. And what causes this, or what causes this in the model, is that as you increase the number of conjunction units that are competing, you are increasing the amount of inhibition that has to be overcome in order to generate a motor action. And so that's what gives you this kind of delayed reaction time. And this is very similar, I should say, to kind of explanation in terms of stochastic accumulators that was given by Usher and McClelland a long time ago. Okay, so what now finally to feature-based attention. In order to account for some of the findings in feature-based attention, I did have to modify the model somewhat, but it's only a very minor modification. And the modification was just the addition of a second timescale of Hebbian plasticity. And really all this did was it just provided a bias so that the model didn't completely forget things that were done a long time ago. And so there are lots of findings in the feature-based attention literature of cross-block congruency effects, for example, which is what I'm going to talk about in a moment's time. And that requires information to be carried from block to block in a way that if you just had this very short timescale of Hebbian plasticity, that would just get washed away. And so this longer timescale, it's identical to the model before, except that now we've got kind of this long timescale plasticity that's an order of magnitude slower than short, W short, which is exactly what it was before. And I should say as well that this modification doesn't actually mess with the model in any way. It's still very much capable of performing all the same working memory tasks. Okay, so this is a feature-based attention paradigm that I adapted from, it's a type of from kind of a paper by Jay Jackson. It's exactly the same type of feature-based attention paradigm that people in Alex's lab use all the time and people all over the literature use. And so the idea is that you'll have a stimulus. Here, it's just this very simplistic thing, a color and shape, but you'll have 2 features. And depending on the rule, you'll have to make a perceptual decision based upon one of the features while ignoring the other one. And so here you have to encode either shape or rule, and that will be paired with a particular motor action. And really the way that I did this was, so I basically co-activated, as I did before in the perception, in a decision-making example, co-activated a input unit or a feature unit, say here green, for example, with a motor action. So it might be left, and that's so just for simplicity, I've got green in the feature unit as a green motor output, and then blue in the feature unit as a blue motor output, and that pairing's done. But at the same time, I also partially co-activate the irrelevant feature. And what that means is that the binding between, we've got a full binding between one stimulus feature and a partial binding for another stimulus feature. And that means that both of the irrelevant features will get feedback from the conjunction units, and that will drive competition and inhibition between these two, keeping them at a very low firing rate compared to the kind of attended feature. Okay, and so when we do this for both color and shape, there will be a particular combinations that will give rise to a congruency effect. So in this case, green and square both map to this green motor output. And so when you get green squares after a few trials, you should, both the irrelevant feature and the relevant feature should drive the same congruency, should drive the same motor unit, right? And that's indeed what we see. So we do see an increase in reaction time, just as we see in the empirical literature. And so all I've talked about so far is behavior. We've got these nice fancy little plots, but it would be really nice if we could kind of link these things to something that we might actually be able to measure in neuroimaging. And the way that you do this is actually really rather simple-minded. All that you have to do is you take the time series that comes out of these feature units and conjunction units, and you pass it through a linear classifier in exactly the same way that you would if it was MEG or EEG data. And if I then kind of, in this case, I've sorted the neural activity just by whether it's task relevant or task irrelevant, i.e. whether it was kind of the selected rule or the non-selected rule, and then ran it through a linear decoder. And what we see is a massive increase in information, or decodability rather, of the relevant over the irrelevant feature. And this is indeed what you see empirically. This is a very well-known finding. It occurs all over the multiple demand regions and across visual cortex as well. Okay, and so just kind of by way of a conclusion, what I hope really rather briefly to have showed you is that despite the simplicity of the model, and despite the fact that it's only based upon Hebbian plasticity, we're really able to account for a pretty impressive variety of empirical findings across the working memory, decision-making, and attention literatures. And in a way that actually, I hope, speaks to both behavioral and neuroimaging data. And in so doing so, kind of provides a source of potential novel hypotheses that help link kind of cognitive theories with the type of thing that one measures in neuroimaging. And so if anyone kind of wants some follow-up papers, I'd really recommend these two papers from Sanjay Manohar's group. Okay, and so with that, I will thank you for your time. And please do feel free to email me if you have any questions.
All right, we are badly over time, not because of Christopher, but because of other reasons. But anyway, I think Christopher deserves at least one question, if there is anybody. Anybody that just wants to have some coffee? Well, if there are no immediate questions, and as Christopher said, please email him. And thank you so much, Christopher. It was nice seeing you. Thank you for joining us.
Oh, it was my pleasure. Thank you for the invitation.
Yeah, thank you. Well, thanks, Christopher.